And let's get to it and see this talk title that is very relevant, but also very cryptic, what it means. First, I wanted to share also a little bit more about myself. Since 2019, I joined King, and I'm leading a team where it's focused on research, but we also are looking at long-term, high stake projects where we believe that can bring value to the company through applied AI research. And we also support different part of the company and work very closely with business. I've been around in the AI for a while and with in different domains, and it's quite exciting and interesting to see how you can apply applications of AI, apply different methods from in different applications of AI. Particularly, I think you've heard already, but gaming being a very exciting testbed for many of those applications. A little bit about myself and game and how I got here. So I guess this game says how old I am. But the top two, the top right, is the first one that I ever played. Have you played the Gorillas game? Who has played it? Yay! Now I know who are the same age as me. So it was a very basic game with physics involved, that you give a speed and power, and the gorillas throwing bananas at each other. The one at the top left is the first game that I had to write when I was in university, and I used to play it when I was stressed before exams, and I was very proud. That's not the screenshot from me developing it, but it was something similar. Nibbles. How I got into the AI in gaming is related to RoboCop and my participation in RoboCop, and applying multi-agent system work in football soccer simulation. So enough about me. Let me tell you a little bit about King. Raise your hand if you have played any of King games. Okay, nice. Raise your hand if you have played Candy Crush. Okay, so probably you most likely know most of the things that I'll explain. So King was founded in 2003. The most prominent game or franchise was released in 2012. And we became part of Activision Blizzard since 2016 and part of Microsoft family since 2023. And if you look at our games, we have more than 200 released games developed. We have over 200 million monthly players. And we have studios in Stockholm, Malmö here, Berlin, Barcelona, and London. Yeah, with over 2,000 employees, we work on a lot of interesting game titles. So let's look at the scale. We talked about the scale of players, and monthly players. Let's look at also the scale of the game. I mean, there's a large Candy Crush Saga is part of a large family of games. And just to think about the size, it has over 19K levels currently and keeps growing. So I think most of you are familiar now about the game. It's a match-3 puzzle game. It consists of sequence of levels, so it's called the progression. As you interact with the game, you play levels and you continue and go through these different episodes with different themes. There are also some side elements where, for instance, you can have social elements, or you can have some purchases of different items in the game. But if you look at the dynamics of a level, there's an objective that, like, for instance, you want to collect dropped elements, or you want to remove jellies from the top of the board within limited number of moves. When you match 3 or more candies horizontally and vertically, they disappear from board, and they cascade, like, random elements cascade from the top. And if you manage to basically match more than 3, you get the special candies that they have a stronger power and, like, have effect over larger parts of the game. There are also sometimes some more complex dynamics in the game. Unlike, for instance, like, conveyor belts and portals and this kind of things. Okay, so what about the game? Our games wouldn't be what it is without our players. Our players are diverse. Some of them started playing yesterday. Some of them started playing back in 2012. And players have different player preferences. They have different skill sets. And we want to make sure that we serve joy to all of our players. So all players want to have an exciting challenge. And how do we address that? So if we want to translate it to a problem formulation for our research, we are talking about delivering the right experience at the right time to the right player. And now, what does that mean? If we think about game experience, like, mainly it comes from 2 levels and players. And I want to here talk mostly about actually the player side and then connect it into the level side as well. In my team, we are looking at research around representation learning. We are looking at causal machine learning, graphs learning. We are looking at reinforcement learning for gameplay, which Sarah, one of my team members, will talk in more detail about it. And then we also look at generative models for content generation. So I'm going to focus on player representation learning here. So what is representation learning? Let's say you have a few data points, and this is a raw representation on the right that we have of our space of samples. And what we want to do with representation learning is basically transform that to a space that gives us a better semantic representation that helps us to describe semantically the space. And usually this representation is also lower dimensional, which helps us also to have an easier way of using these embeddings or representation as an input to other systems. So what are the things that are nice about this representation learning? So first, reduces dependencies on domain-specific knowledge, and you're trying to make consistencies. You create more abstract and generalized patterns from your data, and it can also help for transfer learning when you want to, like, move to different problems, or, like, on maybe out of distribution data when you are building your models. It can also help with enhancing interpretability and performance of downstream tasks that you are trying to solve with your data. So in particular here, we are interested in learning a representation of our player behavior that are generalizable to multiple downstream use cases. So what are downstream use cases? For instance, it could be about we want to predict engagement of players, or it could be, like, building a recommendation for a player, or actually understanding our players' activities better. So why this could be of interest for us? It helps us to have a unified way of representing players. Imagine that, like, we have a lot of different features in the game, and for each of these, you might have like one or two machine learning models, and like, you will go off and build your own model, training data, and like a lot of feature engineering work that goes there, and sometimes there are inconsistencies in the definition of the features that you would use in those models. So here, we want to have a unified way of representing players. We also want to have an enriched context. Very often, features that are describing players in machine learning models, they are aggregated. I don't know, activities in the past 7 days, or number of collected elements in the past 1 day. These are all aggregated. While if you look at, let's say, sequence of raw events of experience of the players and build a representation out of that, it could be much more enriched. And we want to also, of course, improve the performance on those downstream tasks. As I mentioned, also we want to make sure that we have a consistent way of describing our players for different parts of the game. So, wrong direction. How does experience of a player look like in our backend? So, when player interacts with the game, events are sent to our games. And here is, for instance, an example of a mock event. So for each game, we have player ID, which is non-identifiable, and then it's when it happened, and which level it was, why the level ended, what was the score when the level ended, and so on. This is one example of a mock example of an event. And to give you a perspective of the scales, we're talking about billions of these events. And of course, that means that we have a lot of data that we can use in order to understand our players. And if we look at the event data ingestion, so we have the data from the client being sent into the game server. We have a Kafka that helps with ingestion of data, and then we get the data into cloud data warehouse, and then here we have few different types of processes that is happening on our data, like aggregated view of collecting financial reports, and then there's also some aggregated features that are used for machine learning models that I mentioned earlier, like for instance, count of game rounds last week, or maximum level achieved, and so on. And those are fed to machine learning. Here, we are not looking at these two big blobs, orange blobs, but rather we want to use the raw events and use that in order to create a representation of our players and feed it into machine learning models. So, yeah, I mentioned that in our use cases, these are the type of the features that we are looking at. This is a traditional way of looking at downstream tasks. So what we want to do is that in addition to those, some of those features that are quite meaningful, or the current state of the player that we receive, we want to use those representations combined and be able to have better performance on our downstream tasks. Now, what does those embedding look like? And how to obtain those embeddings? So embeddings are basically numerical vectors, right? How are we going to create those? Before getting into that, let's also give you a little bit more context about player events. Player events include for instance, tapping, swiping, the starting of a level, ending of a level, or purchases. And these events, if you think about player behavior, they are irregular, and they are sparse time series. So you don't come back with first of all, not all players are the same, but also you don't have, we don't observe similar patterns in in our players on daily basis, for instance. And there's a long-range temporal dependencies across these sessions. And this part is also important to keep in mind. So we're not only looking at yesterday's behavior, but rather we might need to look at the past 1 month, for instance, as a long-range dependency. So if we look at events together, you sit in the bus, you play candy, you leave at the stop that you want to leave, and within that you have certain number of events and interactions with the game, and that is a session. So you leave. If you're leaving, for instance, let's say more than 15 minutes, that declares a session. We collect that data and we say this was a play activity for 1 session. In one of our research, basically we are looking at these sessions, and let's say we look at the past K sessions of the player in order to be able to look at the temporal behavior of players. I mean, we believe that this structure and breaking down into sessions could be a meaningful thing, because it also describes intentions of the players and some meaningful signals about differences between events that happens, let's say, in this session versus the other session, the next session. These sessions come into our data stores, and they are translated into tabular data. So now the question is that how we can build a representation out of this, we can build a tabular representation out of this stream of events. So here is a research work from my team that we looked at how can we build a good representation out of this data. And we are looking at transformers here. We are looking at encoder transformer, and we want to give an input. The problem here is that this input, as I mentioned, is quite sparse, and we need to find a way to fit this into the memory in an efficient way to have a long context of our players. Also, there's a lot of different types of activities and a lot of different elements, so there's a high variance into values that you can have for each of these elements. So in this research, what 2 of my team members worked on was structuring this into, first of all, for categorical values, encode them and compress them, but also get rid of non-zeros value in the way that represented the data. And they feed this into a BERT-like model where we are trying to solve a classification task. And for instance, looking at, can we, based on distribution of previous sessions, predict the upcoming sessions in the specific window of time. So our learning from this was that actually working with this data is quite hard, and we need to deal with the sparsity, and there is a lot also sensitivity on what kind of task you want to solve in order to get a good performance out of this model. In another research, we started looking at the sessions. Okay, before I continue, I'm going to pause here. Do you have any questions? Because it might, I assumed that you're familiar with transformers, and I assumed that you're familiar with events and so on. I made a lot of assumptions up to here. I was hoping that I get a question I didn't get. So anyone?
Thank you.
Yeah. Okay, so here, I think I kind of mentioned this, but basically we are looking at talking about sessions. We are looking at, can we treat this as a language problem? So basically we take all the events, and what we are doing is that we are processing the event. Like here you see an example of, yes, Here you see an example of data. To simplify, we just like retain relevant events, not all of the events, and then we started like dropping on informative fields, and then you see here like example of informative fields, and then like we did some conversions, grouping by players and sessions, sorting them by timestamp, and then joining the events as a string, feeding this into our model as a string problem, as a language problem. Here we use mask language modeling. Basically what we did was that we got a task of, again, like predicting engagements of like, for instance, if looking at the past case sessions, looking at like in the next 1 week whether the player comes back, and then we started using long transformer in order to make a prediction. Here you can see a representation of TSNE representation of generated embeddings, and we try to simplify, remove a little bit of the noise to make it easier to analyze. And what we did was also we started building a fingerprint of interesting features that can describe behaviors, and see if we can identify fingerprints of our players in each of these clusters. And we see here, for instance, we took away one that was significantly small, so you can here see 8 clusters, but I'm just not showing one of the clusters that is very small. But basically we have 7 clusters: competitive devoted, casual devoted, persistent devoted, leaning casual, economy aware, leaning casual, persistent casual, and persistent collector. Then we went and talked to our teams in the games and also to user researchers, and these seem reasonable, meaningful, aligned with what they've observed. But in order to be able to actually use this at the scale and in production system, for games to use it for reasoning, it of course requires much more work. It requires more user research studies. But it's just an indication that I wanted to share with you that we saw that we can find interesting patterns out of analyzing those embeddings. So this was okay, interesting output, but still we were struggling with getting good performance out of the model, and there was a lot of assumptions and removing data and bucketizing. So we started looking at actually time series. That's a third different way of abstracting. So if we move here, yes. So we are looking currently as different intermediate abstractions, looking at numerical time series. We are looking at event time series, and we've been also looking at dynamic graphs. And these are the research areas that we are currently exploring. Sorry. And what we are doing is basically in our research, we take the data and we are doing benchmarking on different tasks to see, compared to actually you build a model for that task, whether they are performing better, and we see currently promising results, but it's a work in progress. Now, I talked about player representation. I also want to talk about the as part of game experience, the second part, which is levels, and how this connects to player representation. Sarah, my colleague, tomorrow will talk about how we apply reinforcement learning for playtesting in our games to validate the quality of our games, and how we are looking at the research on human-like generalizable playtesting. But I'm going to briefly touch about these parts as well as the introduction to her talk. Getting back to player experience, and that they all want to have a fun, all of our players want to have fun, exciting challenge. We want to make sure that we provide the right amount of challenge, right? If it's too easy, it's boring. If it's too difficult, it's frustrating. So when we are doing level designs, it's important for us to get this difficulty, experience difficulty or experience challenge right. If you think about the process of creating content and delivering it to our games, so it starts with like, ideations, we create the level, we do, like our teams do a lot of test and tweaking, and then when they are satisfied, then they release it, monitor it, and like, optimize it. This process is a lengthy process, and it takes, like, of course, like, planning and creating is quite fun, but like test and tweak is a lot of time consuming effort for our creative team. And what we are trying to do is to help them by automating this part to be able to focus on more creative stuff. And this is more like, we are trying to build an assistive tool for our designs. What we have in production currently is a supervised learning-based model that is playing the game automatically, provides insights about the gameplay to our designers. Under the hood, we have, we represent our board as like, stack layer of different elements. We also have, from our gameplay data of our players, we have corresponding actions on the board that they take. And we try to learn, given a state of the board, what is the most human-like action that the players take. It's a quite complex system because of, like, again, like, sparse representation we have here and large space of actions. We trained this model given the data that we had from our players, and we see that there's a reasonable correlation between, here. So if you look at the bot success rate, and if you look at the player success rate on log the scale, we see that there's a good correlation between them. The easier the level is, it's more aligned, and the more difficult it becomes, it gets less aligned. So there's a interesting research question for us is like, how can we help and improve the playtesting performance for more difficult levels and levels that they have complex dynamic. Here is an example of the gameplay that is done by the playtesting bot. So designers basically design a level, press the button on the playtesting. Here is you see a video of the bot playing the level. And when the playtesting is done, okay, we see some statistics about, for instance, how many moves was used, or what was the level difficulty, perceived difficulty. This is a mock visual, by the way. If designer is not happy, says like the level was too easy, then goes back, designs again, tweaks, and then now you see the difficulty has increased, designer is happy, release this level. Here, we see also the similar process, like in the batch. Let's say you have some levels. Again, these are mock. Designers comes and say that, okay, I'm not happy with this level difficulties. I'm gonna tweak them. I want to change the range of the difficulty of all of these levels that I've designed. Send them to the tweaking system. Under the hood, tweaking system, these are unseen levels, or iterated levels. Designers send it to tweaking agent. The tweaking agent under the hood send this to the playtesting bot, and the playtesting bot gives an assessment to the tweaking solution in order to say, based on these statistics, this is the quality of the level, this is the perceived challenge, and then the tweaking solution keeps editing and provide the answer to the designers. So, yes.
So where does it get the tweaks from? Are these random changes?
No. Um, okay, sorry. Tweaks
Of the levels.
of the levels. Okay, there are two answers to that, yes and no. So the first answer is that, first of all, sometimes the tweaks are manually made by designer, and then they want to get an assessment of the tweaks. Then the second is that sometimes they design a level, but then they look at the performance and they want to see alternative that adjust the difficulty. They send it to a tweaking solution. The tweaking solution is an evolutionary solution, so that's why I said random. Yes, maybe.
Yes. So that's what I meant. The mutation part of it.
Yes. So it's an evolutionary solution. It starts off from created level, and then optimizes based on the constraints of the design principles that we have, and the inputs that came from designer of what are the constraints that what kind of change they want to have.
So the constraints are in the mutation or in the fitness function?
Both.
Okay.
So, and then depending on what kind of constraints we are talking about, so it's if it's a design constraint, it's one that it goes to mutations, and if it's if it's constraints that comes from designer, and this kind of changes needs to be made, then it's in the fitness function. So, at the end.
But the main fitness function is the difficulty metric.
Not just difficulty. It could be more things. Like, for instance, we want to reduce shuffles or bad experiences. So they have certain type of bad experiences that they want to add it to that fitness function. It's a little bit of handcraft work of feature engineering work to make that fitness function work, but it works in closely with designs. But most of it comes from the perceived difficulty. Now,
this is a search-based PCG thing that's actually productionized.
Yes, yeah. So that was actually a demo of actually production system. Under the hood, then the playtesting bot actually evaluates and provides difficulty and a few other metrics to the tweaking solution. So as an input to that fitness function, and then keeps generating new content.
Very cool.
So now I wanted to give you a perspective of how level generation works in and editing of the levels work in at King. It comes with some challenges. I talked about players having different skills, having different preferences, having different context of and expectations from the game. And what a playtesting bot is giving us is an average number. This average player doesn't exist. So ideally, you want to have context feed into this playtesting bot. So how can we capture this context of our players, describing our players, to the playtesting bot? And then another aspect is also that these hard levels with high difficulties, they're hard to crack for playtesting bot, the current playtesting bot. We want to generalize over a wide variety of game content, all of these different complex game dynamics. And we want to use this playtesting bot for evaluating unreleased levels. Sometimes we introduce we continuously innovate and create new game elements, new game dynamics. And if we don't have playtesting data, then it's hard for playtesting bot to be able to generalize and work on those. So that's where we started exploring reinforcement learning, and Sahar will tell you in detail what exciting work we are working on there. So let me skip the reinforcement learning part, but maybe the gist of it is that what the reinforcement learning agent does, and again, Sahar will talk about this, is maximizing a reward. It interacts with the game. It looks at the state, makes an action, and looks at the maximizing a reward. What's a reward, for instance? We want to win a level, right? And then it learns how to win the level. So in principle, if you have the right model and right reward function, if you let it play and interact more and more with the level, it learns how to play and it learns how to win. But the thing is that we don't really want a bot that wins all of our levels. We want a bot that plays human-like. And that's a research that we are trying to figure out. This is where we are trying to combine reinforcement learning and representation learning together to inject embeddings as an input to our reinforcement learning agents. So we started from like human-inspired reward shaping. We built a representation of players' gameplay as a prior to the model, as another part. And then we started looking at prompting the reinforcement learning model on encoded style and preference of the players. And that's like an active field of research that we are looking at currently. So again, we want to have a generalist playtesting agent. So we can put, let's say you have an agent, an RL agent, that learns how to play, and you can inject prompt that I want to condition this RL playtesting on this particular style or difficulty. Let me get into here. So at King and research at King, we started from, let's have one model on the generalization part that fits all. Then we started looking at preference groups, skill groups, and we started looking at research for player context. And now we are looking at how to inject and incorporate this on understanding of our players, improving solving downstream tasks, and also improving the play testing for content generation. What's next on the horizon for us? So just before this talk, we were talking with, we were discussing with David. It's we talked about fitness function now. What's the right fitness function? What's the right optimizing function? We are talking about loss in models. We are talking about optimizing a function mathematically in machine learning and AI. So here in gaming, we are trying to solve what is and describe what is fun. So an area of research that we're particularly interested in is looking at metrics describing player experience and how we can connect this to our research. We also want to have a richer understanding of our players, and we are also in a bit further on the horizon, we are trying to connect all of this together, potentially with word models and generating experiences. I'll get to this point. And finally, I touched a little bit on in-context reinforcement learning, where you prompt and condition on context of the player. On word models and generating experience, yes, I have here the slide. Yes. Okay, so just very briefly, are you familiar? Please raise your hand if you're familiar with word models. Okay. So for the rest of you, briefly, you know about generative video models. This has become particularly interesting to look at word models in gaming, because what you do is that you don't just generate the next frame of a video, but rather, in addition to video, you're also taking an action as an input. You predict what would be the next state or next generated video, let's say, if it's a video game. So let's say you start from one particular frame or like a state of the game, and then what you can do is that let's create different sequences of gameplay. This could be interesting because you can condition it on player style, you can see different outcomes of a gameplay, and you can start basically generating levels with more context about your players, looking at simulating experience of the players and gameplay. So that's an area that we are hoping to touch in near future. Now, final note. So, game and AI, quite fun. we know generative AI actually unlocks a lot of opportunities in gaming. I touched about new sources of data to understand players, different ways of abstracting those, looking at event streams, looking at embeddings. Uh, this way of looking at the data also allows like to bringing different modalities together and understand our players better. However, I also want to highlight that choice of approaches depends on the game, processes, and opportunities. Games are challenging environments to crack, so it's still unsolved problems. If you search a little bit about like can VLM solve gaming, you find a lot of interesting recent work from the past couple of months. And the integration of AI from research to production is actually also a journey of cross-collaboration efforts. And finally, it's all about creating a fun experience. I want to thank my amazing team. I'm presenting basically their work. I do the talking now, but they do the heavy lifting. And again, I want to also highlight the challenges and the only thing that makes it possible is the cross collaboration between research and games. And that's it.